welcome to this program, Gaining a Cosmic Perspective, our new place in the universe with Dr. Scott Fisher. I'm Laurel Westendorf. I'm part of the programming team here at the Deschutes Public Library. Every month, we offer a variety of programming for adults, and we have a great lineup of free programming this summer. If you want to check out other programs we have, you can go to deschuteslibrary.org/calendar or pick up an event guide in your branch. If you have questions for Dr. Scott Fisher at the end of the presentation or even throughout, sounds like Scott was pretty open to that, go ahead and put them in the chat as they pop up, and he's going to stick around for a Q&A at the end. He's a faculty member of the University of Oregon Department of Physics, where he teaches introductory level astronomy and serves as director for the undergrad studies for the department. And I'll let Scott take it away. Thanks, Scott.
Thanks, Laurel. Well, hi, everybody. Thanks for coming today. I was speaking with our colleague earlier. This is the second time that I've gotten to present for the Deschutes County Libraries. And the last time, gosh, it seems like 100 years ago. It was, I think, in 2017 or 2018, where I got to do an in-person presentation at the main branch in Bend. And so I'm happy to be back, and we're going to do a virtual talk today, and then later on in the summer I get to do another in-person talk. So today the title of my talk, oh gosh, there's a couple different versions of the title, but one of my favorite ones is Welcome to Class, Here Comes Your Cosmic Perspective. And what I'd like to do is talk to you today a little bit about the scale of the solar system and to really help place us in the universe. And the way I like to start out all of my talks is with what I like to call a picture of the day, or a pretty picture. And I think we got a good one today. You can see the beautiful vista on that I'm showing you right now. It turns out that is a picture of the Sisters Mountains that we're all familiar with. We're looking from North Sister towards Middle Sister and South Sister. And our gentleman, Mark Lofgren, who took the picture, I don't know Mark, I found his pictures on the internet. And but I did read the story, and 3 times Mark climbed to the top, almost to the top of North Sister, to get this photograph for us. And as you might be able to see, there's some wonderful astronomical connection. That's the disk of our galaxy, the Milky Way, lined up just perfect with the slope or with the peak of South Sister there. And twice Mark climbed the mountain and got clouded out, and third time was the charm. He ended up getting this beautiful picture for us. And actually he has 2 versions of the picture. And in the second version, it's annotated. And I thought this is kind of neat. If you can see, there was some labeling put on the image, and you can see where Middle Sister is and South Sister. I also thought it might be neat to point out to you that over here is the glow of Eugene. And so even though we're about 60 miles away from where Mark was on top of North Sister, you can very prominently see Eugene. And then even more prominently is the glow of Portland. And there's Portland, even though it's about 100 miles away. And that's not so pretty as light pollution. And then we can see that sort of encroaching on the sky. Let's not worry about that too much and concentrate on this beautiful vista of the Milky Way coming just straight up out of Middle Sister. And I think it just highlights 2 things. One, that we have some beautiful environment here in Oregon. And secondly, the dark sky is part of the environment that we live in. And I think that it is it's particularly in Central Oregon, it's something that we need to preserve. And I think that we can do it just like the beautiful outdoors that we have, and we have mountain biking and skiing and all that, the river and other stuff. The sky is part of the environment that we have there in Central Oregon. So I'm going to tell you not too much of a secret. Well, pinky swear you to secrecy right now. All of the slides that you're going to see in my talk come from my Astronomy 101 class that I teach here at UO. And so they're recycled, but for a good reason. And it's because I want to give you the same sort of glimpse into our universe that I try to give the students in my class. And this is something that I show them on the very first day of class. What is one of my goals for the class? And that is to, oops, let me knock this over, is to give the students a scientific view into the universe that they live in. And I like to do it again in a fairly general way, and we can share our awe and wonder of the universe really through imagery. And this is a photograph that was taken by a gentleman named Wally Pachoka. We call it the Wally picture. And I use this particular picture throughout the 10 weeks of my class. And if I do my job right, at the end of the 10 weeks, they know a lot more about this photograph and what they're looking at than when they started at the beginning. But I would like to point out that that here in this picture, the building on the right side is a very large telescope facility, and this is out on top of a mountain in Hawaii called Mauna Kea. And you can, again, you might be able to see the beautiful disk of the Milky Way here going along where my mouse is. Here it's fairly horizontal. It has to do with where we are on the Earth. We're a lot farther south down in Hawaii than we are here in Oregon, but also the time of the year. And this was taken at a different time of the year. So anyways, one of my goals is to give you a scientific view into your universe here over the next 40 minutes or so. I also thought that I would start out this talk with a little story of our lecture. This is more for me than for you folks, but to keep me on point. And what are the things we're going to talk about today? Well, we're going to talk about all my favorite things. This cosmic perspective check that's coming. I also love to talk about planets in our solar system and these exotic planets called exoplanets that we'll talk about. Then we're going to talk about my third favorite topic, me. I'm only half joking about that. But look, let me give you a 5-second introduction to me, and then we'll stick around. And if anybody has any questions, please feel free to hold them to the end. Or if you're feeling bold, I've got the chat window open. And if you are savvy and can use the chat, that sounds great. Just throw a question in there, and I'll see if I can see it. As a matter of fact, let me make sure that's set to everyone, and I should be able to see any comments you put in there. All right, so what's this about? About my first favorite topic is astronomy. And here's another one of the slides that I showed the class on the very first day of class. And look, I believe in my heart that all of us are astronomers, a little bit. Some of us a little more, some of us a little less, but we all have some astronomers in us. And it's because astronomy is deeply embedded in our lives. It's so deeply embedded, we don't even think about it anymore. And if you look, here's just a couple little ways. Hey, how do you tell how old we are? Well, by how many times we've orbited around the sun, right? How many years old we are. How do we tell time? It turns out that the most accurate clocks that we know of are astronomical objects called pulsars. And by the way, even as fundamental as when are we humans, when are we generally active? Well, we're active during the daytime. And the daytime is when our star, the sun, is visible in the sky. When are we not so active? In the nighttime, when the sun is down. And by the way, when the sun is up and down is determined entirely by the Earth rotating on its axis. And so to me, it feels like astronomy is really a big part of our lives. We just don't think about it very much. And I'd also like to say this comment up here. I think that we all realize that science is cool. As kids, we know it. I mean, let us all think back here. What when we were little kids, what did we love? Rocket ships, dirt, bugs, trees, animals, picking stuff up and figuring out how stuff worked. Humans, we're all scientists inside. Now, I do think it gets scared out of us sometimes, mostly by middle school. But look, the point is that we all have a scientific interest in us, and often for humans we have a very deep interest in astronomy. And look, and I can imagine that all of us have been out in front in a nice dark area, and you look up and you see a beautiful moon in the sky, or maybe a nice dark vista of stars, and and we feel it in our hearts. And I think that awe is something that we all can feel. And I also like to sort of make sort of a semi-joke with the students that look, if I do my job right over this 10 weeks, I get to teach you some astronomy. And at the end of this class, I want you to promise to find a significant other, a blanket, some beverages of your choice, and a nice dark sky. And you take that blanket and whoosh, flop it out on the ground with your significant other. You all have a beverage of your choice or two. And if you do it right, astronomy might pay you back in a wonderful way. And so look, share your knowledge that you've learned with your significant other, and heck, you might even get a smooch out of it, that sort of thing. And so the point being is that we try to get folks excited about learning a little basic astronomy. And part of that, I think, is a cosmic perspective. So look, let's talk about, oh my gosh, hold a sec. Let's talk about my second or third favorite topic, me, for a second. And again, keep in mind, these are all slides that I'm showing to the students on the first day of class. And I really like to make the point to them is that I was them some number of years ago, where that number of years is now 30. But I was a state school boy. I went to a community college where I got a 2-year degree. And then I went and enrolled in the University of Florida. And the University of Florida is an exact equivalent of UO, a big flagship university, a state school university. And then there's lots and lots of other words on this slide. Don't worry about them too much. What I would like to say is that I'm a proud duck. I also am very neutral against beavers. I got no problem with the beavs. Now we can always bond on our mutual dislike of Washington. And so, but anywho, I'm a proud duck. There's a picture of me and the duck that was taken a few years ago. And I'm proud to say that over the years, my relationship with the duck has deepened. And this is a funny picture. This was taken in 2019 when I got to be a guest coach with our student athletes at a football game. And I got to spend the whole day with the athletes. I ate breakfast with them in the morning, went to practice with them in the morning, and then got to watch the game from the field, which was pretty darn neat. And it was pretty cool standing here because while I was standing down there, this is the student section behind me. I got a bunch of Dr. Fishers yelled at me from some of my students that were in my class at that time. So that was a really neat experience, but just wanted to show you that I am very happy and very proud to have the University of Oregon on my CV now and on my resume. But it turns out that I had a first career, before I came to become a professor here at UO. And that is, I was an astronomer, a staff astronomer at a large telescope facility called the Gemini Observatory. And at the time, this was in the late 90s and early 2000s, up to about 2010, as a matter of fact. That was the 4th largest telescope in the world. And so really, I spent about 15 years observing at the largest telescopes in the world, the 1st, the 2nd, the 4th largest. I either worked there or observed there. And so I'm real proud to say is that I have a lot of experience observing at big professional observatories. Then I had a little mini career in between that, where I lived in Washington, D.C. for 3 years. And during those 3 years, I worked at a place called the National Science Foundation. And the National Science Foundation is the arm of the U.S. federal government that funds science. And I worked in the realm of astronomy, as you might imagine. And I'm also proud to say that I awarded about $40 million in grant money in the 3 years that I was in Washington, D.C. And many of the programs that I funded were programs that were related to education. Student scholarship programs or summer research programs for students. How do we get young ladies and folks from underrepresented groups involved in astronomy? How can we get research scientists to engage with students, graduate students and undergraduates in their research? And so again, that's something I'm real proud of. And boy, let me tell you, if you want to be a popular astronomer, hand out $15 million a year in grant money. Everybody is very excited to talk to Dr. Fisher at that point. I was even more popular than I was in high school. That was a fairly low hurdle to jump, but still, I was a very popular guy during those 3 years, as you might imagine. But I'm also very proud of the work that I did to be able to fund these projects, many of them which are still going on now 10 years later. So look, what happened is after Washington, I was on my way back to Hilo, Hawaii to work at the telescope, and I heard about University of Oregon and stopped up here and never left. And happy to be here in UO and in Oregon now. But I did want to sort of harken back to my old career for a minute and show you a picture of the telescope that I used to work at. And this is a photograph that I took of the Gemini Observatory up on top of Mauna Kea out in Hawaii. And you might notice this beautiful blue sky. We used to call that Mauna Kea blue. And you knew that when you went to the observatory and you saw a sky like that, all systems go, you're going to do some great observing that night. And actually in this photograph, you can see the telescope inside the dome. The telescope is this structure right here, and it's pointing straight up right now in this particular photograph. But more importantly, I wanted to show you how big the telescope is. And it turns out that one of my colleagues is in this photograph right now. Her name is Naibi. And I promise you, she's a full-size human being. She's like 5'9" or something like that. And she's in there. And let me give you just 5 seconds to see if you can find out where she might be. That's supposed to be the Jeopardy theme song. It's not very good. I'll tell you what, let's not tease you too much. Hold on a second. Oh, let me click this button. There she is. Hi, Naibi. And you'll notice she's waving. That's after I yelled up. I said, Naibi, you have to wave. We can't see you. Let's go back a frame. There she is, standing right there. So just to give you an idea of how big this monster telescope is, there you can see a human being standing in next to the dome and next to the telescope. And again, I can't resist. Here's a couple little fun facts about the telescope. Don't worry too much about them, except I would like to bring 3 things to your attention. And one, that telescope's almost 75 feet tall. So look outside and look at a fair-sized fir, Doug fir, or maybe a nice oak tree or maple tree that's out there in your yard or on your street. And that telescope is probably at least as tall as that tree. And astronomers, we measure the size of the telescope by how big the mirror is inside the telescope. And the mirror inside Gemini has a diameter of 27 feet. It's a funny thing to think about. Gosh, a piece of glass 27 feet across. And to kind of bring that home a little bit, that darn mirror, that thing weighs 22 tons. Just the glass in the mirror weighs about 22 tons. And over here on the right side, you can see a computer drawing of the telescope, not a real picture, just a sketch by the computer. And that mirror is depicted by this bright orange circle right here. But I wanted to do you one better. I wanted to show you what the mirror actually looked like. And so there's a picture of a fine young astronomer standing in front of his telescope. By the way, you'll notice the strong forehead is still there. This is probably 2009, 2009, or 2010 or so. And that's me. And I know you guys, you'll just have to trust me when I say I'm a fairly tall dude. I'm about 6'4". But that's me standing in front of the telescope. And in this particular picture, the telescope is tilted, so it's sort of coming out of the frame. But I did just want to show it to you. You can see where my cursor is right here. It's actually tracing the size of the mirror. And so, gosh, there's a guy that's a little over 6 feet tall, and there's how big that mirror is. And I just really love this picture. I haven't seen it in a while, so when I was looking through the slides today, I got a kick out of taking a look and showing you just how big the telescope is. So, and again, now that's a monster telescope. That's the 4th largest telescope in the world. And you might ask yourself, well, Fisher, how do you use that telescope? And well, there's that guy again. Yeah, looking good. And but this is me operating the telescope. And what you notice is what I'm not doing is sticking my eye next to an eyepiece and actually looking through the telescope. That's because there's no eyepiece on that telescope. As a matter of fact, I don't think any human being has ever looked through that telescope. Instead, on the back of the telescope are digital cameras. And some of the technology of the cameras is the same technology that's in my digital camera right here on my phone, just sort of, super duper versions of the technology that we have in our phone. And so to operate that monster telescope, it's actually quite fun. You get to sit in a control room that's 3 stories underneath the telescope in a building that's down there underneath the telescope. And let's see, what does it take to operate this telescope? 1, 2, 3, 4, 5, 6, 7, 8 monitors, 2 computers, a laptop, 2 mice, there's one, 2 ink pens, and your trusty calculator. And actually, so when you're operating the telescope, you get to sit there in a nice warm control room, and I bet you there's a cup of coffee sitting around there. I can't see it right now this second. And if I were to click the button on this mouse, the picture that the telescope takes shows up right there on the screen. And so not only do we get to operate the telescope from here, we also get some real-time feedback on the data. Boom, as soon as you take the picture, you see it right on your screen. A lot like taking a picture with your cell phone. You take the cell phone and of course you see the picture right there. And so this is, again, I hope just a little bit to give you an idea of what it's like to operate one of those big monster telescopes. And so it turns out that to be a modern astronomer, you also got to be fairly computer savvy, right? You got to be able to sit down in front of these big complicated computers and click around with confidence and know what you're doing. But you know what? It's darn neat, and it's fun. It's work that doesn't really feel like work. You're so so engaged and loving what you're doing. It's kind of a neat thing to sit there in front of all these monitors and operate that. Oh, so Alexandra just asked a question about what type of software do we use? It turns out that most of these screens that you can see, those were custom written. Those were software that was written by a team of engineers that works at Gemini. But some of that software is also kind of off the shelf. Now, this is not a Windows machine, it's a Unix machine, but or Linux, don't worry about that so much. But this screen that you can see on that I'm sort of highlighting right now, that's an app that one could download and put on your Mac or your PC, and heck, and you could use the same image analysis software that the professionals do at the big telescopes. And I'm happy to talk about that more if you want some specifics, but that's a great question. Thanks for asking that. All right, I don't think there's any more pictures of me. Maybe there's one more there later. We'll see or not. But let's move on. Let's move on to a second topic. And let me see real quick the Q&A. Oh, good. I saw a little one up there, but we're good. All right, folks. Tray tables up, seat backs forward. This flight's about to take off. I'm not sure where we're going, but we're going to go somewhere cool. One of my favorite pictures of the solar system. It's not a real picture, but these are models of the planets. And what I really like about this particular picture, one, they're very well done models. These are computer generated models of the planets, and they are to scale. Now, is Jupiter really big enough to fit in your hand? No, darn well it's not that big. It's a lot bigger than that. But the relative sizes of the planets are correct here. And let me count them off for you. If you can see my cursor, there's Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And you might notice there are 8 planets. Not Pluto got the boot. I'm just picking on Pluto. I'm a big Pluto supporter, and I'm happy to talk about Pluto and why it was not demoted, it was promoted into a whole new class of object. But let's just talk about these 8 planets for the moment. So here's what we call the 8 major planets in the solar system, and all of those planets are to scale. And one thing I like to sort of point out right here is our Earth, our entire Earth, would fit just nice and snug inside the great red spot on top of Jupiter. And if you wanted to, you could take about 8 Earths and fit across the diameter of Jupiter. And you're already thinking, that's pretty impressive. 8 Earths. I mean 8 Earths, it turns out, yeah. But you're like, well, wait a second, Dr. Fisher, hold on. What you're missing part of the solar system. Yeah, Pluto, we know about that part. But you're also missing something else big. Where's the sun? Let's bring the sun into this whole situation. Are you ready? Nope. Here comes the sun. There's the sun. This is the exact same models of the planets. Now the sun is there. And look down here. There's Earth. And by the way, you can see right next to him, that's Mercury, Venus, Earth, and Mars, Jupiter, Saturn, Neptune, and Uranus. And by the way, there's Pluto. Pluto's back on the plot right now. And there's the big monster of the solar system, the sun. And this is what I like to call our first cosmic perspective check of the term, just to be able to see the size of the planets compared to the size of the sun. And if you take anything away from this whole me blabbering on today, one thing I really want you to remember is that 109 Earths will fit across the diameter of the sun. Look at this tiny little Earth right here. And you could take 109 of those Earths and make a beautiful little, sort of necklace of little beautiful blue marbles, of little blue Earths. And it would take 109 of them to go across the diameter of the sun. Let's have a dramatic pause for a moment. That is really something to think about. Now, don't look at the sun. Oh my gosh, one of my recurring nightmares is somebody is going to look at the sun and they're going to say, Fisher said, look at the sun. Don't look at the sun. So we're not going to look at the sun, but At sunset, the next time you're out at the coast, or maybe you see the sun setting down over the mountains, just glance and keep in mind that that thing that you see in the sky, that beautiful ball that we call the sun, is actually 109 Earths across. And I got to tell you, it takes a little while for this to sink in. You got to do it 2 or 3 times. Don't look at the sun, but take a glance at the sun when you can, and imagine 109 planet Earths. Have you ever even thought about 109 planet Earths before? If we were in a room together, you all would be doing this right now. And of course you haven't. Why would you ever think of 109 Earths? There's one Earth. But to think 109 of them across the front of the sun, that's something. But you also got to keep in mind the sun is just a star, just like any other star out there in the sky. Now, it's our star, which makes it special, but it's just like any other one out there. Let me show you this next thing. You all might know where this is. Turns out it's a place where it never rains. I know if you're a duck, you know all about that. So I love Google Earth, the program Google Earth. Everybody go and look at Google. Go look at your house on Google Earth. It's awesome. So I was surfing around Eugene one day looking at Google Earth, and I saw Autzen Stadium. By the way, this is where the Ducks play. This is Autzen Stadium here at Eugene. And I thought, well, how big is Autzen Stadium? And it turns out in Google Earth, you can measure distances. And I don't want to do it right now, but I promise you, if you click right on this scoreboard and you draw a line across Autzen Stadium to that scoreboard right there, it is 665 feet. 665 feet. Anybody remember how tall I am from that slide earlier? About 6'4". What if I told you I did some math for you? What do you think 6'4" times 109 is? Damn close to 665 feet. Folks, if you took 109 of me and laid me tip to tail all the way, 109 of me would fit right across the diameter of Autzen Stadium. First of all, let me make a comment. If there were 109 of me, we would band together into an army and we would rule this planet. Very benevolently, I'd like to say, no, I'm just picking on that stuff. 109 humans will fit across the diameter of Autzen Stadium. And I think you know where I'm going with this. You, compared to a stadium, is the same as the Earth compared to the sun. And I think that's something, again, that takes a few minutes to sink in. And I even give the students an extra credit. I say, then you go to Autzen for a football game, and when you're standing there in the stands, I want you to have a moment of zen where you think of crazy old Dr. Fisher telling you that you, compared to that stadium, is the same as the Earth compared to the sun. And I really like that comparison because I think it helps us sink in and it helps us really kind of grasp this difference in scale that we're talking. And so I just really like that idea. And there's the one thing I want you to go and impress your friends and family and significant others that with you. Like, again, astronomy will pay you back if you share your knowledge in a good way. You don't have to trust an old ball guy on that. So look, there's a couple other fun facts about the sun here on the slide. I'm not so worried about them, but I do think one thing that's pretty neat is that if the temperature of the sun on the surface, but you'll notice those air quotes, it's not really a surface. The sun is actually gaseous, but what we perceive as the surface has a temperature of about 6,000 degrees Celsius, about, maybe 10,000 degrees Fahrenheit. But just to kind of give you, again, just sort of a sense of, just a number that helps ground us compared, to what the characteristics of the sun is like. Don't worry so much about that distance thing. We're going to talk about that in a second. So you compared to Autzen is the same as the Earth compared to the sun. So remember, don't look at the sun, but take a glance at the sun one time. And here's what I thought was coming, right? When I said about the star. And keep in mind that our sun is just a star. And by the way, it's a very average star. It's sort of a C student. It's not too big, not too small, not too hot, not too cold, not too red, not too blue, right in the middle, kind of a Goldilocks thing. And our sun is a star, just like every other star that you see on this picture right here. And I sometimes in the class, I like to tell them, I like to think that there's a bizarro Dr. Fisher that is given a lecture on a planet around another star. And when they look up in their sky, you know what our sun looks like? That one right there, or maybe this little one over here, or maybe our sun would in their sky would look just like a star in our sky. And again, I think that's kind of a neat thing to sort of ponder. Lots of stars up there. Now, last warning, don't look at the sun. But remember, now you know a little bit more about that thing up in the sky when you see it. And I urge you to take a moment and the next time you see the sun low in the sky and that beautiful red orb, that you can look up there and you have a little better feeling about just how massive that thing is up in the sky. And I think that's a darn neat thing to share. Let's hold on a second. So, the sun is a star. We know that. Many, many stars up in the sky. I want to show you a neat thing that our friend JP Matsab-Anio did. And JP he's a person who is 3 times cool, if you ask me. He's an amateur astronomer, a computer programmer, and a photographer. And JP realized that humans, our eyes, we have a difficult time discerning that the sky is actually 3-dimensional. You know, it looks like we live under a dome. Of course it does. Now we don't, but it looks like we do. And so what he realized is when we see a beautiful astronomy picture like this picture right here, that often we can't perceive that it's 3-dimensional. So this is a real astronomy picture that was taken in the sky, and JP figured out a way to make it do this. Oh, golf clap for JP. Well done, JP. He wrote a computer program that takes that astronomy picture and just rotates it back and forth. The amazing thing is by adding movement to the image, it tricks our brain into seeing it as 3D. And now you can see these stars, for example, these 3 right here are closer to us. The nebula, which is a massive cloud of gas and dust, is in the middle of the frame. And these stars back here are back behind it. And just by rotating that image back and forth, it's a trick. It tricks our brain into seeing that as 3D. And he's done this for a couple different photographs. Here's another one that's pretty neat. Right here in the middle is a cluster of stars. And those stars are so bright and so energetic that they're pushing away all of the material that they've formed out of. And it turns out they're actually carving a little bowl out of the side of this massive cloud of gas and dust is there. And if you sort of cup your hands, maybe make a little cup in your hands and imagine that the palms of your hands were painted turquoise. That's the shape of what you're seeing right there. Let me see if I can sync my hands with it. Oh, I'm doing it backwards, but I'm rotating the cup just like it looks like in that image. And those stars are carving a bowl out of the side of that nebula. And then JP, he did one more of something called a star cluster, a globular cluster. Oh, JP, oh, well done, sir. And so again, not again, but this is a cluster of stars, and there are about 5,000 individual stars in a cluster like this. And all of those stars are orbiting each other, kind of like imagine bees flying around a beehive. And then that whole unit is orbiting around our galaxy called the Milky Way. That's something called a globular cluster. And I show you those just to sort of give us, again, just because they're cool and I can't resist sharing them. But at the same time, this is to make sure that we can have a feeling that when you look out in the sky, and tonight, you all didn't know you were going to get a homework, but I'm going to give you a homework. And your homework is, I think it's going to be clear in Central Oregon tonight. Go out, let your eyes dark adapt to go up and look at the sky, and keep in mind that all of those stars that you see are also in 3D and are at different distances from each other. Love it. So look, I want to tell you a little bit about this scaled solar system, and then we'll talk about exoplanets for a few minutes, and we'll be done. I probably got, I might got 15 more minutes, maybe 20 minutes total. So look, here's another nice one cool thing that I like to teach my class, and that is again a model that helps us grasp how big the solar system is, and interestingly, how far away the stars are. I think this is a neat one. So look, you can read the slide. What we want to do is create a scaled solar system. And so we're going to take that massive thing, the sun, and shrink it down by a huge factor, by a factor of 10 billion, which is 10,000 million. Don't worry about that number. That number is a little hard to grasp. What we want to do is shrink the sun to the size of this lovely grapefruit. It's not a grapefruit, it's a softball. So let's shrink the sun down to the size of a softball right here. By the way, I had a student that painted the softball for me to look a little bit like the sun. Well done, Andrea. Thank you very much for doing that back in the day. And so let's take the sun and we're going to shrink it down to the size of the of this softball right here. And then I'm going to ask you a question. Now, you guys, I thought you folks are lucking out, because I thought I would be able to see your smiling faces on your little windows, but I can't see them today. So I'm gonna ask you to play along anyways. I asked these questions in my classes, and by the way, I generally teach big classes. I had 350 students in the last class that I taught, so it's me in a massive auditorium full of students. And what I like to do is I'd like to make them do things in class, even 350 of them. And one of the things we do is called a chest vote. And that is, I put up a slide like this on the big screen and everybody can see it. And all the students have to put their answers. But you know what's really hard to do? Put your hand up in front of 350 people. So instead, we have them pick 1, 2, 3, or 4, and they put their vote right here. And that way I can see their selections, but nobody else can. So here's the scoop. If you're feeling bold, you're welcome to put your answers in the chat so I can sort of get a feel for what y'all are thinking. But here's the first, if not, I'm going to tell you the answer here in a second anyways. But look, if we shrink the sun down to the size of this softball right here, how big is the Earth on that? Oh, and I see some folks are going for it. I like it. Diane, you were first. You would be one of my faves. Is anybody else thinking that they're being bold? I'll give you this again. If I had the Jeopardy theme song here, I would do it for do 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 do. Oh, look, even Laurel jumped in. Yeah, I like it. I like it. We got a spread. We got 1s. We got 2s. We got a 3. Yep. It turns out you got Diane got it. It's the size of a ballpoint pen tip. And by the way, I've got a pen right here. And right there at the very end is a tiny little ball. And so if you might imagine, thank you, Marilyn, you got it a pen tip. About 109 of these little pen tips would fit across the front of the sun. And by the way, you all might get a kick out of this. When I first started teaching, I did not say pen tip, I said BB. And because I thought it's the size of a BB. You know who does not know what BBs are? College students these days. And the reason I figured that out is I had a foreign student, a young lady from, oh gosh, she must have been from Japan, I think, in my class. And we wrote an essay and she wrote, the sun is the size of a softball and the earth is the size of a BB. And in parentheses, she put a baby bee. Oh, a baby bee. And of course, it made me realize she did not know what a BB was. So we switched to a pen tip. And now when I do this in class, we make sure that the sun is the size of the softball and the earth is the size of a pen tip one there. All right, you guys, you did good so far. Here's one a little more challenging. On the same scale, the sun is the size of a grapefruit. The earth is the size of a pen tip. How far away would the earth orbit the sun on this scale? Let's see what the folks are thinking. Oh, Alexandra's in. Alexandra's in with her selection. this is fun for me sitting here. I'm sitting here right now. I don't even know how many of you are out there, and I'm thinking, I'm like, oh my gosh, I didn't know there was going to be a pop quiz. I promise, no points up. And our friend Laura was like, I don't know, I'm not going to guess. I'm just picking. But I think I think I might have made you. Alexandra, you almost had it. It's about 50 feet. So, a look in the room. Oh, Marilyn came in with 5 miles right at the end. Good guess, girl. Not quite. So look, imagine the little grapefruit at the corner of the room you're in, and then imagine something about 50 feet away. For me, it would be sort of the other side of my office. If you're in a good sized room, maybe the two rooms away or outside your window, in your yard somewhere. But on this scale, the Earth would be pretty close to the sun, only about 50 feet away. And by the way, I also did a little calculation for us. And what I discovered is on this scale, the whole entire solar system would be just about the size of the UO campus, which is not real big. You think in Bend, let's see, what would this be? If you were standing, if you were standing at the top of Pilot Butte and the sun was right at the top of Pilot Butte, the solar system would not be too much bigger. If you put maybe 3 by 3 Pilot Buttes, something like that, like the downtown, the whole solar system would be about the size of downtown Bend. And I'm thinking downtown, is Wall Street and Bond Street and kind of, that area right there down in downtown. So if we put this grapefruit right in front of the tower theater, then the whole solar system would be about the size of downtown Bend. Not too bad. All right. Crack your knuckles, get stretched. You ready for one more question? No, it doesn't matter. It's coming anyways. On the same scale, how far away is the nearest star? And by the way, that star is called Alpha Centauri. It's our neighbor star. So this is again, kind of one thinking that, the solar system is about maybe the size of Bend or downtown Bend. How far away is the nearest star? Alexandra's feeling bold. She's in. Oh, we got another good one. We got Laura was in. Marilyn, you gotta guess this time. I like it. You guys are better than my class. You know what? You got it. 2,500 miles away. Look at this face. Folks, that is something. By the way, congratulations to Marilyn and Alexandra. You got it, number 4. A glowing softball right here in Eugene, Oregon, and the nearest star is in Washington, D.C. What? That is something. And by the way, that's our neighbor star. It's about 2,500 miles away on that scale. Remember your homework? Tonight you have to go outside and look up and see the dark sky. Every star that you can see tonight with your eyes is at least 5 times farther away than that. And some of the stars you can see tonight are 100 times farther than that. And even if you can see some really faint ones, they might be 200 or 300 times farther away than that. That is an incredible thing to say. Our nearest star, boom, glowing grapefruit here, glowing grapefruit in Washington, D.C. And then the things you can see up in the sky tonight are 50, 10, 50, 100 times farther away than that. And that's, again, one of those things that takes a little while to sink in, but I think it's kind of a neat thing to ponder once in a while. So you did good. Heck, you know what? Everybody gets A's, and an A plus to Alexandra because she went for every question. Thank you so much for taking part. So let me talk about planets for a few minutes. If you give me 10 more minutes, 15 minutes at the max. And this is my favorite planet. My favorite planet in the entire universe, as far as I know of right now, is Saturn. And Earth is 4th on the list. 4th is pretty cool. But Saturn by far is my fave. And this is a picture of Saturn taken by the Cassini spacecraft. And I love Cassini so much, I'm actually going to write it out. There's how you spell Cassini, Cassini. Your second homework is to go to Google or Yahoo or your favorite and type in Cassini mission and learn about Cassini because it's awesome. So anyways, Cassini was a spacecraft that orbited Saturn for about 10 years. And this is just one of the thousands and thousands of pictures that, and ChatGPT too, yep. Or ChatGPT it. And it will, but this is a picture that we can't see from Earth, because this is if you can see the backside of Saturn and the beautiful rings. I would argue that this is one of the best photographs of Saturn that's ever been taken. The spacecraft was right there, beautiful resolution. And by the way, this is true color. Saturn is this kind of, I find it very interesting, sort of a, cream gold sort of color. And so, yeah, it's just a good picture of Saturn. Saturn's not purple and pink. This is the best picture of Saturn that has ever been taken from Earth. This was taken by the Gemini Observatory, that telescope I used to look at. And it turns out that that's a big telescope and an excellent site with very high-tech cameras. This is about the best picture of Saturn that has ever been taken from Earth. And by the way, down here next to Saturn, you can see one of the moons of Saturn named Titan. Real quick, Saturn is not purple and pink. This is a real true color. This is what our eyes would see if we could see Saturn. Here, this was an infrared picture. And our colleagues, Emily and Henry, who took this picture, they photoshopped it, scientific photoshopped it. They made it purple and pink to show that the material in the rings is different than the material that makes up the planet. The planet is a gas giant. It's made of hydrogen and helium primarily, but the rings are made of ice crystals and little tiny rocks. It turns out the rings, we think, used to be a moon that got too close to Saturn, and the moon got broken up by the gravity of Saturn. That's a different lecture. Let me come back. I'll give you that lecture on that next time. So, best picture of Saturn ever taken from Saturn. Best picture of Saturn ever taken from Earth, right? This is a telescope on Earth. This took a picture of Saturn. What if I wanted to show you the best picture of Earth that's ever been taken from Saturn? There it is. That was taken by Cassini. Here's Saturn. There's the rings of Saturn. Anybody want to guess where Earth is? I bet you can see it right there. That's us. That's every human being that is alive, and every human being that has ever lived is on that little spot right there. Our little, as Dr. Carl Sagan said, our little blue marble, the blue spaceship that we're all riding as we fly through space. And I got the heebie-jeebies right now. This picture just really affects me like that, to think that every one of us right now are on that little thing right there. And that's what Earth looks like from Saturn. That's what we look like. And by the way, here's a couple little background stars that you can see also, but that's us. And by the way, I know that one person in this talk right now is actually in the photograph. And were you in the western part of the United States, Hawaii, Japan, Australia, or South America in July of 2013? If you are, you were in that photograph, because that's the face of Earth that was facing towards Saturn when Cassini took this picture. And I know for sure I'm in the picture, because I knew on July 19th, 2013 at 1:27 in the afternoon, I walked out into the middle of the quad on the UO campus and looked up in the sky right where Saturn was. I waved. Yes, I did. I waved right at it, right when they were taking the picture. And I just thought that was kind of a neat thing to think about, that there was a spacecraft pointed back at us taking the picture right here. So I urge you all to go to Wikipedia and type in the day the Earth smiled, and this page will come up and you'll get to read all about this project. And if you look down here in the corner, There's a 1,600 different pictures that folks submitted. I did not submit one, but there's a photo mosaic of this particular day. So look, I love this so much. I'll go through it one last time. This is the best picture of Saturn ever taken from Saturn. Here's the best picture of Saturn ever taken from Earth. And here's the best picture of Earth ever taken from Saturn. And again, I just think, again, to give us, again, this cosmic perspective and this little scale that we're talking about, that's a pretty darn neat thing to be able to look back and see our planet just from Saturn, as a matter of fact. Oh, look, and here's I think this is my final Saturn picture. This is just another photograph that Cassini took, and the sun was directly on the other side of Saturn. So this is kind of a solar eclipse from Saturn. And you can see the rings are being backlit by the sunlight. And again, this is an image that a photograph that we could never take from Earth. It took Cassini being out there at Saturn and literally on the opposite side of Saturn to be able to get this backlit view, which I thought was pretty cool. So look, talking about planets, let's talk about exoplanets for a few minutes. And again, I got another 10 minutes and I'll be about done. So look, what's the definition of an exoplanet? An exoplanet is a planet that's orbiting a star that is not the sun. So these are planets that are outside our solar system. And I think this might be interesting for this particular group too. The very first exoplanets, were discovered in the 1990s. That is not that long ago, folks. I mean, it's absolutely amazing to me that the students in class they've been alive. We discovered exoplanets their entire lives. They've lived, and we've known about these exoplanets. That just shows me how quickly that this field is changing. In another way to show how fast it's changing is I started teaching in 2012. And in 2012, we had discovered about 1,000 of these planets around other stars. And every time I taught this class, I looked up how many exoplanets we had discovered. And by the way, as you can see what's going on, the number is increasing dramatically. And every time I taught the class, I updated the slide. And by the way, as of today, there are 5,438 planets known around other stars, around stars that are not the sun. And by the way, I gave this talk in April, and look, there was 5,322 in April, and now we're up to 5,438 here in June. So in just 2 months, we've discovered over another 100 of these planets. And this is one of the amazing things is that now we've discovered enough of these planets that astronomers are starting to be able to do models and build models of how these exoplanets exist. And the current theories suggest that basically every star in the sky has, on average, one planet around it. Lots and lots of stars have no planets, and some stars like our own, by the way, we now have 14 planets. We've got 8 major planets and 6 dwarf planets in our solar system. So we've got 14 planets, other stars have none, but if you average them all together, roughly every star in the sky has one planet around it. And there's the third part of your homework tonight. Go outside and look up in that beautiful Central Oregon dark sky, look at the stars, and now you can envision that every star you can see on average has one planet around it. And that's a pretty neat thing, I have to tell you. You should be very proud that we're alive during the times that we've discovered these exoplanets. And I'll make a case for that in a second. So basically, we've confirmed now 5,400 of these exoplanets. And I can't resist. I'm going to go for it. I'm going to click a YouTube and let me see. Can you guys, Alexandra, somebody let me know. Can you see the YouTube? Can you see a YouTube video on my screen right now?
Yes, I can.
Yeah. Thank you. Thanks, Laurel. And yes, Marilyn, yes, all of those planets are in the Milky Way. These are all in our Milky Way. And so look, let me show you this little video. It's a minute. This is a picture of the entire sky, the northern and southern hemisphere. And watch as I hit play here. Each little circle you see is a place that we've discovered an exoplanet. And you can see the year and the number, and I'll try to be quiet. I can't resist. So even in 2005, we only knew of 150. And the big finale? Lovely. Oh, I just love that video. NASA, yeah, you guys did real good. I look at this. These planets are everywhere. They're all around the sky. They're in every direction that we look. We're starting to discover them. And you might ask yourself, Dr. Fisher, what the heck is going on right here with this big purple patch? That's where a mission called the Kepler mission, Kepler. The Kepler satellite was launched, and its entire goal was to look for exoplanets. And that's the part of the sky that Kepler looked at, that little part of the sky. And by the way, if you go outside tonight and you make a circle with your fingers like this, that's about how big in the sky that image that where Kepler was looking. But I love this video because it just sort of shows you that we're finding the planets everywhere. Basically everywhere we look, we're finding these planets. And I really think that's a neat thing to do. Now, for how much of the Milky Way, Marilyn, you asked a perfect question. All of those planets are in the Milky Way. And how much of the Milky Way have we searched? Only these two little blue triangles. That's it. And we found 5,400 planets in just this teeny little fraction of the Milky Way that we searched. And by the way, these are hard things to find. And so we need high technology to do it. That's why we've only searched a teeny little bit. But I've got one more little model for you. And how much of the Milky Way have we searched? If you take our whole solar system and shrink it down just to the size of a quarter, the entire solar system, then the Milky Way galaxy would be about as big as North America. And by the way, not just the US, that's Canada and Mexico also added in there. The Milky Way galaxy would be about as big as the entire North America. And how much of it have we searched? Oh, we've searched about the size of Connecticut, it turns out. So not very much. And I also learned that Lane County is almost the exact same size as Connecticut. So we've searched only Lane County compared to the entire continent of North America. And we've already found 5,400 of these planets. So you might imagine as we search more and more of the galaxy, we're going to find many thousands more of these planets. And I like to argue with the students that, look, 10 years from now, we'll know of 50,000 planets outside the solar system. I'm almost done. Look, these planets, we can't see any detail on them. The only thing we can see are these tiny, there's a planet right there. There's a planet right there. Here's a system that has 3 planets around it, HR 8799. So we can't tell what they're made of quite yet. We can't tell what's on them, but we know they're there. And I think this is the last slide. And here's my big finale. I sometimes like to think of the far future. And to me, that's maybe 1,000 years, 2,000 years in the future. What's going to be happen in 2,000 years from now? And my opinion is it might be 1,000 years from now before humans, we're starting to think about going to the stars. It's going to take that long for us to develop our technology, and maybe never we can do it. But I think 1,000 years from now, and everybody on this talk right now, we should be very proud of our generations, because we are the folks who are discovering these planets for the first time. We are making the map that future humans will take to the stars. And to me, that's a very profound thing. And I think we should be real proud that it's our era that are making the maps that folks far in the future will use to go to planets outside our solar system. And so look, that's it. Oh, there's one last picture of me. There is me and 3 of my students standing up at Pine Mountain Observatory. And by the way, Pine Mountain is open in the summer. and we'd love to see you all up there. And so look, that's it. Thanks for sticking around and listening. Thanks for the good questions. I appreciate the interaction with you all. And I'm happy to stick around and do some Q&A. But thanks everybody for attending.
Thank you, Scott. Let's see. Does anyone else have other questions for Scott, or a stump the astronomer question?
Yeah, those are fun, but don't be too mean. No.
What do you do mean? Says, I bet you could.
Oh, Diane had a good question. How do we detect exoplanets? You know, there are several different ways. Most of these have been detected by what is called the transit method. And imagine if this is a star out there, and it's got a planet orbiting in front of it. Sometimes those planets will orbit right in front of their star. And when they do, the planet blocks a little bit of the starlight and the star dims. And that's how we're detecting these planets. We're watching Kepler, that satellite, could see about 100,000 stars in the pictures that it took. And Kepler was so precise. It took one picture every minute of that same field, literally for 5 years. And it could detect when each of those little stars had the little dips in front of them. And that's how that was that most of the planets were detected. When they move in front of their star, they block a little bit of the starlight. We can measure how big the dip is and how long the dip takes, and actually learn quite a bit about the planets from that. There's also a few different ways to do it. I'm going to type a link into the chat right now. It's called exoplanets.nasa.gov. And if you go there, they have some wonderful illustrations and little videos that show you not only how we've detected them, but what we know about the planets too. Oh, Alexandra asked more about the software. Is it primarily coded in Python? A lot of the software is coded in Python these days. There actually is another, I happen to remember that some of the other, like the screens you were seeing, those were actually, those are in something called TKL, CL, I think it's called TKLCL. And there's a homework for you. Look up that Linux-based program called TKLCL, and that's how they literally created the push button screens, the interface, the GUI that you can see on those screens. But if you're curious, right now Python is by far, oh, there you go, that you're an experienced coder. Python is by far the most common language being used in astronomy today. And by the way, since you know the talk, check out astro.py is a wonderful library of Python routines that are already written out there. That'll get you started for sure.
Awesome. Oh, is there another one there?
Oh no,
Okay.
she's it. Thanks. Yeah.
Awesome. Thank you so much, Scott. This was wonderful. You're a great.
Oh, you're
teacher.
welcome. Thank you.
So-
I'm really happy to be back. I really appreciate my partnership with the libraries, and I'm looking forward to our next event in the not too distant future.